Chapter 26, Quiz B. First question, local school vending machines offer a range of drinks. So we have 4 categories of drinks. And the purchasing agent thinks that each drink is equally favored among the students. These numbers here are the recent purchasing choices from the vending machines as shown in the table. Is the purchasing agent correct? That is, do the students prefer these drinks the same? Now we have just one column of data for the 4 drinks, so it's a one-dimensional table. So this fits the pattern for a goodness of fit test, and the expected amount is that the expected count would be for each cell the same, because the purchasing agent thinks the students prefer them the same. Now you can see that the numbers are not the same. Some are bigger than others. Okay, so let's go through the preconditions. First of all, we have categories and we have counts. So we have counted data. Assume safely that a drink selection by one student is independent of another. Assume this sample of 680 students, because it's 680 altogether in the table, is less than 10% of the student population. The expected count for each cell is 170, which is greater than 5. Assume this is a random selection of students. The preconditions are met. We will use a chi-square goodness of fit test with 3 degrees of freedom for the sampling distribution. The null hypothesis. The types of drinks are equally favored by the students. Alternative hypothesis. The types of drinks are not equally favored by the students. Okay, so we'll go to Stat and Edit, and there's the numbers 159, 198, 174, and 149 in L1. And L2 is simply 680 divided by 4, which is 170 for each. So if you added up 170, if you added up L1, you get 680. If you add up L2, you get 680. All right, so then we're going to go to Stat and Tests, and we'll do the chi-square goodness of fit test. And we hit Enter. The observed is in L1, the expected is in L2. The degrees of freedom is the number of cells minus 1 for the goodness of fit test, which is simply a one-dimensional test. Okay, I hit Calculate. So the chi-square statistic, which corresponds to the t-score or the z-score, that is, it's a number of standard deviations, is 8.01. The p-value is 0.045. That's barely below 5%. So we're going to say that we achieve significance. Now the CNTRB, that's how much each cell contributes. So the first cell is lemon lime. It didn't contribute very much to the statistic, 0.7. It's sort of hard to read these. It's easier to read them if you use them. It would be easier to calculate these and put them into a table. So anyway, we're going to continue in a second. So with the p-value below 0.05, we reject the null hypothesis. There is evidence that the students do not select the drinks equally. Now the next question is, which type of drink impacted your decision the most? Explain what this means in the context of the problem. Now, in order to figure this out, we need to look at CNTRB. Unfortunately, these numbers are hard to look at on the screen. So what I'm going to do is I'm going to go to Stat, and I'm going to go to Edit. So what we can do is we can make a couple of calculations. Probably the easiest thing to do is to calculate what's called the standardized residual for each cell in the goodness of fit test. Now this is easy to do for the goodness of fit, and here's how you do it. We're going to take L1, so we're going to take actual minus expected. So open parenthesis, I'm going to take L1 minus L2, Okay, and I'm going to divide it by the square root of L2 of the expected. Now what this is going to give me is not the contribution to the chi-square statistic. Instead, it will give me how many standard deviations each cell is from the expected. Now, the first cell is almost 1 standard deviation less than expected. The second cell, which is the strawberry kiwi, okay, is over 2 standard deviations over. So what does that mean? Well, and then the other 2 cells are 0.3 and then negative 1.6. Okay, so the negative 1.6 indicates that the grape drink was drunk less than was expected. But of all the cells, the one with the biggest standard deviation, the one that deviates furthest from what's expected, is the kiwi strawberry. Now, what does that mean in context? You should buy more kiwi strawberry. You know, the people seem to be drinking more of it, so you should probably buy more until the sales go down. So anyway, so that's what you would derive in terms of context from the construction of the residuals. Let me go over that again. So the standardized residuals, let me write the formula out. You gotta want to get them in the right order. So I'll write it on here. Is actual minus expected divided by the square root of the expected. So what I did here was open parenthesis L1 minus L2 divided by the square root of L2. Now I'll do it again. I'm going to clear this column and then hit enter and go back up to the top. And I will do an open parenthesis L1. You got to make sure you do it's actual minus expected. Otherwise your residuals will be in reverse. Your standardized residuals will be in reverse. Divided by the square root of L2. Okay, so there they are. And these standardized residuals correspond logically to standard deviations. Okay, so all right, to counts of standard deviations. All right, so the kiwi strawberry contributes the most to the p-value and the rejection of the null hypothesis that you should buy more of it. Or the purchasing agent should get more. Okay, 2. Manufacturing plant receives shipments from 3 different parts vendors. There's a defect issue with some of the electrical wiring. The plant manager, so here we have defect issue with the electrical wiring and the recreational vehicles. Okay, so the population is recreational vehicles, and the parameter of interest is wiring defects. And here's the issue. Wonders if all of the vendors are contributing equally. All right, so this is the chi-square test of homogeneity. Does one column differ from another? So the question is not does the horizontal variable, is it independent of the vertical variable, but rather looking from the point of view of the columns, is the distribution proportionately the same for each plant? Okay, so if you take the total number of cars coming out of each plant, the proportions should be the same across for each one of these manufacturers. Okay, so that's the test. It's called the chi-square test of homogeneity. Do the columns have proportionately same distributions? Okay, we have counted data. Number 1, that's precondition number 1. 2, the occurrence of an electrical problem in one RV is independent of a problem in another. That can be safely assumed. 498, that's the total number of RVs in the table, is less than 10% of the population. Assume that the quality assurance inspections are sampled randomly. The expected count for each cell is greater than 5. The preconditions are met. We will use a chi-square goodness of fit test with 4 degrees of freedom. That's Now we have a two-dimensional table. We have rows and columns. So we're going to subtract 1 from the rows and 1 from the columns and then multiply them. So we have 3 minus 1 times 3 minus 1, or 2 by 2. So you have 4 degrees of freedom. So we will use the chi-square goodness of fit test with 4 degrees of freedom as a sampling distribution. Null hypothesis. The results of quality assurance tests for each company are the same. Alternative hypothesis. The results of the quality assurance tests for each company are different. Okay, so we run the test. Now, let's look at, so what are we doing here? We use the matrix. I'm doing second and then the inverse key here. And I go over to edit and then A. And it's a 3 by 3 matrix. So I'm going to hit 3, enter 3. Okay, and it goes rows by columns. And then I put in the numbers. And I just put in the numbers as they are presented here, 53. Now make sure if the table includes margins, totals, you don't include those. Just the inner cells, the cell counts. Okay, so double check your data entry. And then once you're done here, you're going to get out. Let's clear the screen, get all that stuff off of there. Okay, then we'll do stat tests, and we're going to arrow down to chi-square. Test. Enter. Observed is A. Expected is B. Okay, enter, enter, and then calculate. Okay. Now, the chi-square statistic. Let's see, did I go through all the... Wait, let me finish going through the preconditions. Assume that the quality, blah, blah, blah. Okay. Oh, one thing precondition we had to look at. Let me just jump in here and do that. We had to check, after we ran the test, that the contents of matrix B have at least a count of 5. The expected, matrix B is the expected count for each cell, not the actual, but the expected. The expected count for each cell must be at least 5. You only find that out by checking matrix B. So let me get out of here. Okay. And the results of the quality, so the null hypothesis, the results of quality assurance for each test for each company are the same. Alternative, that they're different. We run the test. We get a p-value of 0.116 with a chi-square statistic of 7.4 and 4 degrees of freedom. With the p-value of 0.116, we fail to reject the null. There is no evidence that the results of the QA test for each company are different. That the, let's call this the distribution. Okay. And that is it.